Hello and welcome to the ADS Workbench video tutorial series. In this lesson we will go through the setting up of a 3D single row steady simulation. To begin, we must first select an airfoil geometry. We will then initialize the full field, set the aerodynamic conditions, and define end walls and computational boundaries. Once that has been completed, we will then select mesh settings and flow solver settings. Prior to starting the workbench, we must make sure that we have the geometry files already defined. Our sample case is made out of 5 sections. Each section is defined by 128 points and is defined in the XR format. There are many different formats that are available to the user. They can be either cylindrical or Cartesian coordinate systems. You should refer to the technical reference for more information. When defining the multiple sections of a 3D geometry, it is important to note that each section must have the same number of points and be in the same format. Alright, let's get started. First, let's open up a new 3D single row steady case wizard. For case name, let's put row 1, and let's put it under Project Turbine. So step 1 is to define the airfoil geometry data. The first thing here is the name of the AGF file. This is actually really important. Here, our AGF file will be called row1.agf. At the end of the wizard, all of our airfoil and aero and geometry data will be defined in the AGF file, so you do not necessarily have to open up the wizard again in order to get all the information for what was defined in your case. So let's move on. If you remember back to our sample was made out of 5 sections. Each section was made out of 128 points in the XR format. We will say that we will use 20 blades in this row, and let's not have any splitters. It's important to realize here that the splitters is not a total number, but rather a ratio of splitters to blades. Okay. The last thing you want to define here is the leading and trailing edge for each airfoil. What we've found is that normally the leading and trailing edges are well defined and do not need any additional help. However, if this is not the case, the ADS tool suite provides several options to help improve the leading and trailing edge definitions. Here we will import the 5 geometry files that were created earlier that define the 5 sections of our airfoil. It does not matter the order that you import them in, as the span location is explicitly defined in each of the files. The ADS Workbench will do some explicit checking to see if A, the number of points specified per sector, matches with the geometry file specified. And it will also check that the format that the file is in matches the format that is expected. Occasionally, the geometry that you are importing does not exactly match what you want to simulate. In these cases, the ADS tool suite allows you to scale or flip the geometry to better suit your case. The next step is to define any tip or hub clearances that exist in this case. In our sample, we have a 0.02 inch clearance at the tip across the entire edge. It is in inches, and this is defined by the units value that was defined in step 1. Step 2 is to define the flow field. What you see here are defaults for stationary air. You can change them if your medium is different. Step 3 is to define the aerodynamic conditions. We're going to start with the inlet. First thing to do is to select the number of span-wise points that define the pitch average inlet profile. You need at least one, and in our sample we're going to define one at the 50% span. Alternatively, you can import a file if it exists. Also, define the aerodynamic conditions at the exit. Step 4 is to define the computational boundaries. The computational boundaries are made out of 4 points, 2 at the upstream boundary, 1 at the hub, and 1 at the tip, and 2 at the downstream boundary, also at the hub, and also at the tip. Step 5 is to define the end wall. The end wall must be made up of at least 2 locations. Each location is defined by 2 points, 1 at the inner diameter and 1 at the outer diameter. Alternatively, you can import an existing end wall definition. Now that we have the aerogeometry data defined, let's change some mesh settings. The mesh is very important when it comes to aerodynamic simulations. It will define the performance with which the computation completes and the accuracy and precision of the data that is output. The first thing to look at is the mesh type. The ADS tool suite supports many meshes. Right. It is recommended that the user use OHH as this provides a good combination of performance and accuracy. However, if you are used to some other mesh type, you can use those if you need. If you look into the ADS technical reference, you can get more information on each of the mesh types. For our sample case, if we move down, we're going to use a mesh fan out on both edges. And since we have a tip clearance, we will generate a tip mesh. Here we recommend 8x8 as again, it's a combination of performance and accuracy here. The last thing to look at is the mesh granularity. Here it is very important as it helps to define the number of mesh points between the leading and trailing edge of the airfoil, the number of points from the hub to the tip of the airfoil, the points from the upstream boundary to the leading edge of the airfoil, the trailing edge of the airfoil to the downstream boundary, and then the number of mesh points across the airfoil pitch. There are recommended settings, recommended granularities that the ADS tool suite already comes with, ranging from very fine to coarse. If you, however, need more customization, you have the ability to select and enter your own values. ADS recommends using fine. It is a good combination, like the other two, a good combination of speed and accuracy. Let's configure the solver now. The first thing to look at is the flow simulation model. Let's select turbulent flow simulation. The next thing to select is the number of iterations to execute. Here the default is 6,000, but really that data is dependent on the case you are running. Some simulations come to convergence much quicker than others, and therefore it would be not worth the CPU time to be executing the additional iterations. So it is best to run the simulation once, get all the performance data, see at which iteration the data converges, or when the data stops changing, and then use that to execute further simulations. Once you have selected the number of iterations to execute, we have two additional variables called the number of iterations between printouts, which are your performance data printouts, and then the number of iterations between large file generation, things like plot files and restart files. The reason why there are two different ones is because generally plot files and restart files are much larger than the performance data, and they should be produced at a lower interval in order to improve performance of the overall system. Click Finished, and we are done.